2014 Leibniz-Tire level connected particles question, part B. A smooth wedge of 8 kilograms rests on a slope 30, rests on a smooth horizontal surface this time. A particle of mass 3 kilos, this guy, is placed on the smooth inclined face of the wedge and the system is released from rest. Show on separate diagrams the forces acting on the wedge and the particle. And then in part 2, we're asked about the wedge moving 3√3 centimeters, which we'll get to now in a minute. If we look at the wedge, 30, we have a reactionary force, always this wedge between it and the particle, which we'll call R. We have acceleration in that direction, which we'll call A. We have its weight, well, it's 8g coming down. And we also have a reactionary force we called S in a previous question. We call S again between it and the ground, which we're not going to use in this question. Also, we have the particle. Now the particle, 3 kilos. 3, it's going to go down. We'll call the acceleration B. We'll need to get the acceleration relative to the wedge in the next part. We have our 30. We have our 3g. We have our 3g, put the 30 in cos 30. And we have our 3g sine 30 because it's opposite the 30. 3g sine 30. We have our R. And I think that's it. We don't need anything else until part 2. So let's look at part 2. Part 2 of this question, the wedge moves 3√3 centimeters in t seconds. And in this time, the particle moves a distance of x centimeters relative to the wedge. Find the value of t and the value of x. Okay, well, we need our forces equations. Let's have a look at the wedge first. We have this R coming down here, down in this direction. We know the wedge is moving in this direction. We call our acceleration A. So we need to get the force going in that direction, which is opposite to 30. So R sine 30 is going in that direction. So it's the only force here. So R sine 30 is equal to MA. So M, just what was M? 8. 8A. Okay, again, with these questions, the key is the acceleration with the particle relative to the wedge. So we look at that first. We have our wedge is moving in this direction with an acceleration A, and the particle is moving down in this direction with acceleration B. So we need to get the difference between this one and this one to get the downward acceleration. And we have our 30 and our 30. So this is going to be A, it's adjacent to 30, A cos 30. So we also need the one going down this way when we do our forces equation. This is going to be A sine 30. So let's create another diagram with that particle on it. The weight of it was 3. So we have 3g. We've already put these on the earlier one. 3g, 30, 30, 3g, cos 30, 3g sine 30. I have my R. And now I have my accelerations from this diagram here. So let's look at this direction first. This direction first. So going down that direction, we have 3g sine 30. This one here. And that's going to be equal to m, which is 3, by my acceleration, which you can see is going to be b minus a cos 30. and in the other direction, this direction here. So we're starting with our 3g cos 30 because it's not bouncing up in the air, so we can't take it, it's not going in our direction first. So 3g cos 30 minus r is going to be the m, which is 3 times this a here, which is a sine 30. So we simplify these down. Let's take the first one. Sine of 30 is a half, so we have 3g over 2 is equal to, and we may as well, well actually, let me not do that first. I can cancel the 3's here, can't I? Should do that first. So I can divide across by 3. So I'm going to get g sine 30, or g over 2, is equal to b minus a cos 30 is root 3 over 2, so root 3a over 2. I can't divide by 3 in this one, so I'm going to get 3g cos 30, so 3 root 3 over 2 times g minus r is equal to 3a by the sine of 30, well that's 3a over 2. And my r then, I have over here, so we get r in terms of a, r over 2, r by a half is equal to 8a. So r is equal to 16a. So now I can sub that in here. So I'm going to get, well, I want to just get a, so let me bring it across. I'm going to get 3 root 3g over 2 is equal to 3a over 2 plus r 16a. So that's 1.5 and 16, that's 17.5a. So root 3g over 2 divided by 17.5 will give me just a on its own, and if we type that into our calculator, we're going to get 1.4549, so 1.455 ms to the minus 2. That should help me get b. B up the top here we can see b is equal to 9.8 over 2, this one, plus root 3 over 2 times a, plus root 3 over 2 by 1.455. Tidying that up in our calculators, we're going to get b is equal to, we're going to get 6.16 with a couple of zeros, 6.16 ms to the minus 2. Now let's jump back up to the question and see what they're asking us. They're asking us to find the values of t and the values of x. Values of t and the values of x. So we want the time the wedge has taken to move this distance. So the acceleration of the wedge. So the time, we're looking for the time. It starts from rest. The acceleration was equal to a, which was 1.455. And the distance s, well, it's given to us in centimeters. Is it it's 3 root 3, isn't it? 3 root 3. So what's that in meters? 3 root 3 is equal to 5.196 centimeters. So 0.05196 meters. 0.05196. So we're going to use the formula here. S is equal to ut. These are the variables we have, plus a half at squared. So 0.05196 is equal to 0 plus 1.455 t squared over 2. So we're going to multiply 2 by 0.05196. We're going to divide it by 1.455, and we're going to get the square root of it to get t. So what does this work out to be? T is equal to 0.267 seconds. and we're asked to find s. So now we have the time. We're asked to find the distance the particle moves. So the time is 0.267 seconds. We're looking for the distance, which they've called x, so we leave it at x. It started from rest, and the acceleration is equal to b going down the incline, which was 6.16. So again, we're going to use the same formula. S is equal to ut plus a half at squared. So S is what we're looking for. We'll call it S. It starts from rest, so we're looking at a half by 6.16 by t squared, which is 0.267 to be squared. And typing that into our calculator, S is equal to 0.2195 meters. And that's this question complete.